So hello everyone, this is lecture 16 for the quantum mechanics. In the last lecture we were discussing about the expectation values and we have compared it with the average value and we have derived a formula for any operator. You can just place its value here and you will operate your wave function here and here. So that will give you your expectation value. Now see, this is for the normalized case. So we have discussed all the cases for the normalized wave function. If it is not normalized, then you will use this formula. This will be equal to divided by psi star psi dx. Okay, so what is the value of this if psi is normalized? Then this will be equal to 1 and this will again be the same formula this. Okay, and you know this is equal to 1. So when psi d is normalized, this will be valid, and when it is a general case, it will be valid. Okay, so I will recommend you to use this formula in any case. Okay, so this will not give you any error. Now see, we have this expectation value for position, means for any operator this is this. So if it is x for any position, then this will be equal to this. Now what is the meaning of expectation value actually? Okay, so today we will understand a little bit more about the expectation values in the real meaning. Okay, so that is nothing but just the first postulate. So we'll study about the how our wave function collapse and all. Okay, so let's move forward. So expectation value is nothing but average value, and for momentum if we find, then we know what is momentum operator, we will see about it. So we define momentum operator as minus I h cut del by del x psi dx. Okay, so we defined our momentum operator this way. So that's why we can find the expectation value just this way, placing it here. Okay, now what is the meaning of this average value? Means what is the real or the physical significance of this average value if we are finding for the position, finding for the momentum, spin, angular momentum, spin. If we are finding these expectation values, what they represent? Now let's go into the theory. So if you have any particle, then mathematically we have seen that it is a wave packet made up of a large number of monochromatic waves. So they will be k1, k2, k3, means they will have different lambda. So k is nothing but 2 pi by lambda. So they are made up of a large number of monochromatic waves. So this wave packet is form of this. Now what we will discuss that if we operate any operator on the wave function, then that will give us the value of that wave function. So let's say we define our these waves, means this wave packet in this form, because this is superposition of these all waves, and these all waves are orthogonal, or we can call them eigenstates because they are linearly independent. So we can write this psi x as c1 phi 1 plus c2 phi 2 plus c3 phi 3 and so on. Okay, so now when you operate momentum operator on this function, so this will give you any one of them. So what is the meaning of this? That you will get only either phi 2, either phi 3, either phi 1, not all. Okay, so see, if you find means we measure momentum for a particle, electron, and it can be any particle, so you will only get one value. You are not getting any probability or any discrepancy there. You are getting only one value definitely, because that is the particle when you are observing. So when we observe a wave, it collapses to a particle, and that particle can have momentum any one of the here. Okay, so it can be any momentum here. So it's like a dice you have. It has 6 faces. When you roll it, it will take any one of the face, and then the modification is that when you get one face, then other 5 faces will be deleted, means they are just erased. You will get only that face and that will be there always. You can't just roll that dice again. You will get one face and that will be all. Okay, means that's how if you have a wave, then that will collapse to a particular momentum or the position, and that will be all. There can't be, you can't measure that wave function again, means that wave function will collapse on the first measurement. So let's see, if it collapses to the phi 2, then what it will give us. So p operator, we know this is minus I h cut del by del x, and this will be phi 2 is this a exponential I k2x. Now differentiating this will give us what? It will be I p2 divided by h cut phi 2. This I square will give you minus 1, will give you this plus 1. H cut will cancel out, so you will get p2 phi 2. So this will be equal to p2 phi 2. Now corresponding to phi 2, you will get momentum p2. Okay, and probability of getting this phi 2 will be square of this c2, means when you operate this p with psi x and you will get this phi 2 as your particular value, probability of getting this from this wave packet will be square of c2. Now see, after measurement, the wave function collapsed to one of the eigenvalue, as I told you, of operator p, and it will give us this. So this is not a means this is no use, there is no use of this equation to us, because we know if we operate with phi2 we will get the momentum p2 definitely. But point is we don't have this one value, we have a very large number of possible values, phi1, phi2, phi3, phi4, phi4, and we can get any one of them. So what is the use of this? Okay, so any one, phi3 will give us p3, phi1 will give us phi1, p1. So now point is how to find the average value and what is the meaning of average value. So here we were, now when this collapse to this phi2, now if you can't measure this again, so you how you can find the average value if you can't measure this again, because this wave function is collapsed to this function. Now how to find the average value? Because if you check the another wave function, that will be different. Okay, now what you need to do is you will take large number of particles and measure the wave function at the same time, because those ensemble of particles have the same wave function at that time, and they will collapse to different, they can be collapsed to phi1, they can be collapsed to phi3, phi2, and they can be collapsed to any one of them, p1, p3, p2, and p1, p1. That's how they can collapse, and that's how we can find the average of that momentum. So let me give you a more clear idea by position. So what I'm trying to say is here that if you have this particle, then there will be some matter wave, then you are following this particle of the matter wave. When you have a fluorescent screen which will bright up when this fall on that point, means it will give a bright spot at the point where this particle lies. So when the particle is in the air, it will can have the both character, particle or the wave, but when it spot the screen, it will be bright spot somewhere at only one point, not the everywhere, it will be only at a particular point. So let's see, we are getting here. Okay, now at the same time there is another particle which have the same wave function at the same time, not after it. If some it is coming, then we have the same function, we will get same value. So there is no point if we measure after some time, so we need to measure at the same time with the same wave function, because this is collapsed. Now there is no use of this, so this will give here only. But now at the same time we have two particles and the same wave function. Now this can collapse here and this can collapse somewhere here, and there can be third particle also at the same time, and it can collapse into somewhere here. So that is the actual measurement. Now we will get these different positions and we will take the average of these positions, and that will give you your expectation value of position of the particle. This represents the probability. So you will get a, means if you have n particles, then you will get most of the particles here, because the maximum probability is here and some particles here. Now see, if you operate this x position on the wave function, it will give you this, because it is only bright spot at a single point. So you can represent this by the delta function. Okay, Dirac delta. So that is defined for the single point. So it can be written as, if this point is x1, so x delta x1 is x1, because this term will be 0 other than point x1, but defined for the x1 only. So when x equal to x1, this will be 1 and here it will be x1, so it will give you x1. So that's how you can define. Now if it is at the x2, then it will be x2 here. So that's how you will get for same part, means at the same time you will get different values, and that's how you find the average. Means if you get n number of values like this, there are n particles, and for this first particle you get the position as x0, for second particle you get at x01, and for this again x0, x02, again x0. So there can be more than one particle at the same position also. Then you will take the average of them, means this position divided by total number of particles will give you average position. So that is the expectation value we defining. So hope now you understand what is the meaning of expectation value, and how this help to understand the momentum. See what happened in the momentum case. There was a single particle and have the wave. So when this hit the something, or when we observe this, then this will collapse to a particular wave with the particular momentum. Okay, so there will be any one of them only. And now what we will do to measure the expectation value, we will take n particles, and they will have they can give us p1, p2, p3, any one of them. So at the same time we are measuring, so we will take the average of all those values, and that will give us the expectation value of momentum. So hope you understand this thing. Let me give you an example of Schrodinger's cat. Hope you heard about this. So inside the box there is your cat, and there is possibility that eventually it can die also, means cat can die or it can live. So up till when you don't open this box, so there is both possibility, it can die also and it can be alive, but you don't know, it can both nature. But when you open this box, then definitely you will know that it is alive or dead. So it will miss, if we call that box inside as wave function, then after opening it, it will collapse to a particular value, and you can't measure this again because now you know the result and this will remain same always. Okay, so this will collapse either to the alive or either to the dead. So if you open this box, so it can be dead also, so both possibility are there, and there will be probability of that. So that's the same thing he defined here, but there was only two possibility, dead or alive. But there can be, but here in this wave function there can be n phi functions in which this can collapse. Okay, so here we will take n values average, there you are taking the only two values average. So that's how we relate the Schrodinger's cat with this thing, means collapse of wave function. So let's understand this thing in theory. This average value of position means, it doesn't mean that if you measure, means you will having the same particle and you are measuring that again and again. So and taking the average of that will give you won't give you the average value, because you are mostly, if you are measuring for the same particle coming after it, so first wave function is collapsed. Second, if you eventually measure all the points here, so you will get all the positions here, so this will not give you the average value, means measuring for the single particle won't give you the average value. You need to take all the particles at the same large number of particles at the same time to get the average value. So it doesn't mean that if you measure position of any particle over and over again, average of the result you will get, means this will give you your average. This is not the case here. The first measurement whose outcome is indeterminate, means first measurement we did, so it can be anywhere in this range, will collapse the wave function. It will collapse the wave function. So we are giving the reason before this, to a spike at the actually obtained. So it will give a spike here, and the subsequent measurements after this, when we measure for the same point, they are performed quickly, then they will simply repeat the same result. Means if you after this you are getting same positions, means you will get position only here. Means if you are getting single ray of particles, so they all will give you position here. You can see this when you throw or the emit a electron gun, electrons are emitted from electron gun, then they will give you a single dot on the screen. So that means that you are getting a only single position. But if there are n electron guns and you are getting different, then when you observe on the screen you will get different positions for all the electron guns. So that is the case. I hope you understand this thing. Now this is the average of measurements performed on particles all in the same state psi. So that is a different n number of particles all in the same state, and we will perform the observation on them and will get the position, take the average. So this is your expectation value. Now what we will do, we will create ensemble of particles each in the same state psi and do the measurements on all the psi x at the same time and take the average of the outcomes. So this is the same thing I am repeating again and again, so that you can understand this thing, because if you don't understand this thing you can't understand the quantum mechanics. So same for the position, same you can apply for the momentum also. For the different waves you will have different monochromatic momentums, so you will take the average, that will give you your expectation value. So that's all for today. We'll meet you in the next lecture. Thank you everyone.